Hello everyone, I am going to derive the equation by which anyone can be able to get the value of kinetic energy of alpha particle or of the daughter nuclei in any kind of alpha disintegration or alpha decay processes. First of all, let's consider a nuclei symbolized by this capital X having the number of nucleons called the mass number A and the proton number capital Z. Initially this nuclei at rest, so its momentum is zero because it has no velocity, that's why its momentum is zero, and after some time it breaks into alpha particle by giving the daughter nuclei. As the alpha particle have the mass number 4 and charge number 2, the daughter nuclei must have mass number A minus 4 and charge number Z minus 2. For conservation of charge and mass, we have to equate the charge and mass number in both hand side of this equation. So this is a complete equation for alpha decay because alpha is nothing but helium nucleus, bare helium nucleus. If you have helium plus plus, it's called alpha particle. So in this reaction, you are getting alpha particle with daughter nuclei. We don't know what are the values of A and Z, but we know the value of helium nucleus is A and Z, that is 4 and 2. And in this reaction, there will be emitted huge amount of energy symbolized by this Q. And using this Q, we will be able to calculate the kinetic energy with which the daughter and the alpha particle emitted. First of all, we don't know in this case what is the Q value, and we are going to derive a general expression by which you will be able to calculate any reactions kinetic energy taken away by alpha and constituent daughter nuclei. For that, we have to apply the conservation of energy and conservation of momentum. You see, in the left hand side of this equation, this is the initial case. Initially, this particle or this nuclei is at rest. We can say initial momentum is equals to 0. And after that, in this hand side, after the reaction, we can say the final momentum Pf is equals to momentum of this helium particle. We don't know what is the momentum of P alpha, and we don't know the momentum of this daughter nuclei, but we know by conservation of momentum this Pi and Pf must be equal. So for conservation of momentum, we can say this initial momentum 0 will be equals to this final momentum, which is nothing but momentum of alpha particle plus momentum of daughter nuclei. And from this expression, we will see P alpha equals to negative of Py, and in general we will say this P alpha and Py equals to a simple P, because in terms of magnitude this will be equal. This negative represents the recoil particle and the daughter particle will be emitted in different direction. If this is a particle initially and it breaks down into two particles, it is at rest and it breaks down into two particles, then it will be in general that the emitted two particle will be emitted in two directions. That's why this negative sign arises, but momentum wise both the particles momentum will be same. The less heavy a particle is, the more velocity will be taken away by that particle, and the more heavy a particle is, the more less it will be moved away. So this equation would be helpful for our calculation, that is P equals to P alpha equals to P daughter. Now if you apply the conservation of energy, then we can say this Q value will be shared between this alpha particle and the daughter nuclei. That is, we can say this Q value is nothing but kinetic energy of alpha particle plus kinetic energy of this daughter nuclei. Now, what are the values of this K alpha and Ky? We have the expression kinetic energy is equals to P square divided by 2m. P is the momentum, m is the mass of particle, k is the kinetic energy of particle. For that, let's consider this helium nucleus's mass is small m, this daughter nucleus mass is capital M. So this small m and capital M are in general. Small m can be anything, sorry, for helium this small m is 4, and for this daughter nuclei capital M can be anything. So from this expression we can say this capital Q is equals to P alpha square divided by twice of mass of alpha particle, which is small m, plus P capital Y square divided by twice of mass of daughter nuclei, which is capital M, so twice of capital M. Now from this equation we can say this P alpha and Py are equal. So we can take this P alpha Py out. We have capital Q equals to P square. If you take this LCM, we have 2m small m, and at the off side we have small m plus capital M. So this is the expression of capital Q. From this expression we can say P square equals to twice capital M small m divided by small m plus capital M times Q. So this expression would be helpful for our further calculation of kinetic energy of alpha and daughter particle. Till now we have used only two conservation laws. First of all, momentum conservation, by which we had get this value P alpha Py equals to P, and from moment energy conservation we have get this P square equals to this value. Now we know kinetic energy of alpha particle will be K alpha will be equals to P alpha square divided by twice of mass of alpha particle, which is small m. Now if you replace this alpha square by this P square value, you will get, so I am going to replace this P square by this P square, because P alpha square equals to P and P y is equals to P. So we can replace this P alpha square with P square, and we have the value twice capital M small m divided by small m plus capital M times capital Q. This twice small m and this twice small m get cancelled, and we have the expression for kinetic energy of alpha particle, that is K alpha equals to capital M divided by small m plus capital M times Q value. Similarly, if you calculate the kinetic energy of daughter nuclei, so let's calculate Ky equals to Py square divided by twice of mass of daughter nuclei, which is capital M. Now if you replace this Py square with this P square value, because Py equals to P alpha equals to P, so let's replace this Py with P square. We can replace this by P square, and we know the value of P square equals to that. So now let's replace this P square value with that value, which is twice of small m capital M divided by small m plus capital M times Q value. This capital 2m, this capital 2m get cancelled. We have the value for kinetic energy of alpha particle, sorry, daughter particle equals to small m divided by small m plus capital M times Q value. So these two are the expressions for kinetic energy of alpha particle and daughter particle. Small m is the mass of alpha particle, capital M is the mass of daughter particle. Now let's take an example. Take uranium 235. If this disintegrates into alpha particle, helium 24 plus 4 will be, let's name another particle, we don't know what will be the value of, so let's name it 2 will be, so it will be 89 and that will be 231. You see, in this side of the equation, this mass number is decreased by 4 and I am not confirm about the Z number of uranium. It will be 92, I think. So if 92 is decreased by 2, we have 90. You can see from periodic table what is the element corresponding to Z equal to 90, and it's confirmed that the mass number will be decreased by 4, so 231 and Z number will be 90. For this reaction, if you calculate the kinetic energy of alpha particle, K alpha, which will be equals to capital M is here 231, and at the bottom we have small m is small m in this case is 4, so it's 4, and capital M is nothing but 235 minus 4. This is the value of capital M. Here we have considered M is the mass corresponding to the daughter nuclei. So in this case, daughter nuclei mass is 235 minus 4, that is 231 times Q value. And if you calculate this, you will get the result, that is kinetic energy of alpha particle equals to 0.98, around 0.98 times Q value. From this we can say the 98% of Q value will be taken away by this alpha particle or helium nucleus. That means the more light a nucleus is, the more energy it will take during the escape process, and the rest of the energy, that is 2%, will be taken away by this daughter nuclei. So this is the calculation from which we can say what amount of energy will be taken away by alpha particle and what amount of energy will be taken away by daughter particle. So that's all for today's lecture. If this video is helpful for you, if you think so, you can like this video, and if you want this kind of video in future, feel free to subscribe to my channel. Thank you.